Okay, so today we'll be beginning the final topic of the course for this year. That will be light and atoms. Now we're going to start by looking at electromagnetic waves and how those are created and how they are also received by transmitters. But we've got to start by looking at what are they to begin with. So electromagnetic waves occur on this electromagnetic spectrum. So all of these things are the same. They're created basically they are photons of different energy. All right. So all of these things are the same, and you would have heard of all these before. So what I mean by that is, if you have a look down here, we've got gamma rays. Hopefully you've heard of gamma rays before. You've definitely heard of X-rays. They're used to get an image of your bones or parts of your body. We've got UV, ultraviolet rays. So they're used in tanning booths, and now we know they're really dangerous. They come from the sun. We've got visible light, infrared. All right, they're used to see in the dark, amongst other things. We've got microwaves, we use that to heat up our food, and we've got radio waves, which we use to communicate with each other. Now, all of these things, gamma rays, X-rays, radio waves, visible light, they're all the same. Okay, so when you're getting an X-ray done, you're getting just another form of what comes out of the lights that you're seeing from your screen right now, or if you look up at the roof coming out of the light bulb. So that's really interesting. All of these things are the same, and they're a wave, basically. So you see this word, it's called the electromagnetic spectrum. So electromagnetic, what does that mean? Well, let's break it down. There's two parts to it. There's electro and magnetic. Electro refers to the electric field. As you can see highlighted in blue, what one of these waves or photons is an electric field that oscillates. So that's a word we'll come back to. Or it vibrates up and down, just goes up and down and up and down. You can see it as the blue one does. Now at the same time, perpendicular or at right angles to, we've got a red one. So that's a magnetic field, and it goes left and right, left and right. So we see we've got an electric field component, and a magnetic field component. Now, when you get both of these together, we get what we call an electromagnetic wave. Okay, and that travels throughout the universe, depending on if it's visible light or an X-ray, or depending on which one it is. So we say that the wave is sinusoidal. So a sinusoid is just a function that looks like this. It just goes up and down forever. And we have two fields, electric and magnetic, and they're perpendicular. So let's see if I can do this with my hands. One of them goes up and down, and the other one goes left and right at the same time. So we get this going on. Whoa, that's not good, but you get the point. Now, these go up and down and left and right, creating this wave, but the wave travels forward. All right, so we'll have a look at that with the slinky demonstration. But yeah, that's the basic summary of an electromagnetic wave. So electromagnetic waves, I'm going to shorten to EM. So this is electromagnetic. Okay, because we're going to be writing it a lot. All right, you get the point. It's written on the top of this slide here, electromagnetic. We're going to be writing a lot, so you want to shorten it, EM waves. So why do we care? Why do we care about electromagnetic waves? So and they're really important, and I guarantee you're going to care about them in a minute. But what we know is that a charged particle produces an electric field. We know that. So we've seen that when we're looking at electric fields. We also know that a moving charged particle creates a magnetic field. So now we're getting an idea. We've just looked at electromagnetic wave is a magnetic and electric field. And we know that charged particles produce both of these, depending on whether they're moving or stationary. It doesn't matter, but they produce both of these. So that's what we know. We know a charged particle produces an electric field, and a moving charged particle produces a magnetic field. But what do we actually see? So what we see is if we move I'll just move my little head. All right. If we move a charged particle, all right, we see that we produce a moving electric field. Okay, so we're going to introduce this word oscillating. All right, so if you're not sure, oscillating just means moving, so up and down, or left and right, either one, and it just keeps going back to the same spot, and it just does the same pattern over and over and over. So it just oscillates back and forth forever, same spot, or up and down forever. That's what oscillate means. So if we have a charged particle like an electron or a proton, and we move it up and down, what it does is it creates an electric field that goes up and down as well. So by moving that particle, we create an electric field, and it also creates an oscillating magnetic field, and that happens perpendicularly. So what we see is we create an electric field going up and down and a magnetic field going left and right. Where have we seen that before? That's an electromagnetic wave. So we can create these things. And we'll have a look at exactly what I mean there without using my hands in just. All right, so let's have a look at what I mean now. You can see here we've got a little ball over here, and it's going up and down. All right. Now what we're creating in the red we highlighted is an electric field, and the blue is a magnetic field. Now these are the same size, they're just perpendicular. So it's really hard to represent this in a 2D image, but I think this does a really, really good job. So if we oscillate that particle up and down, we get this electromagnetic wave. So we've created one of those. Now, this is another example of that. So again, we've got this charge oscillating up and down, and we created a magnetic field in yellow and an electric field in red. So you can see in both of these that the magnetic field is a perpendicular to the motion, and the electric field is parallel to the motion. So it goes up and down with the charged particle. All right, so next question is, who cares? All right, now I think you care more than you'd like to admit. I care, everyone cares in modern society in Australia. So we can use this to generate electromagnetic waves, and all radio, TV, Wi-Fi, Bluetooth, microwaves, light, they're generated this way. So it's a really important concept if you have ever watched TV. Or if you think you can give up TV, fine. All right. If you think you can give up your Bluetooth, fine. If you think you can give up your microwave, fine. But Wi-Fi is created this way as well. So we'd be in a bit of trouble. But that's why it's really, really important, and they're all created this way. And these are the 3 examples of where we see in real life these waves created. All right, so we've got to transmit the signal. So we've got to get that going. So basically, all of these transmissions are just metal rods or rods that allow electrons to flow through them. So what we do is we put an alternating potential difference across the rod. So maybe we'll make this a positive and this a negative, okay? And if we've got a little electron in there, it's going to want to accelerate to the positive, okay? Once it gets up here, if we switch it, if we now get rid of that, make that a negative, make this a positive, it will want to come back down. And we can get that oscillation happening. So we can create our own radio waves. And that's how we transmit these signals. All right, so this is basically, again, what I've just summed up. So here is what the antenna looks like. So we'll charge either end, create a potential difference, and then our particle wants to accelerate up and down. And then that's how we create that electric field and that magnetic field. So that's just another summary of that process. All right, so this is a really nice little summary of how it's created. And what we see here, the most crucial fact is that the frequency, okay, so how often we put it up and down, it's equal to the frequency of the wave, okay? So when we're talking about frequencies in electromagnetic waves, we're talking about this spectrum here, okay? So the faster we go up and down, the shorter the wavelength, so we'll create more towards the gamma ray side. All right, we don't actually create those in this way, but yeah, theoretically. All right, when we want to create longer waves, we go up and down slower, so the frequency is a little bit slower. Now, when we are listening to the radio and we put it on whatever station you listen to, it represents, those numbers represent the frequency in megahertz. So when you're tuning into, I don't know, if you're listening to, say, Nova, it's 91.9. So that's 91.9 megahertz. Okay, so this thing is oscillating 91.9 million times every second, so that and then your antenna is tuning into that oscillation frequency, and that's how you pick up the signal. But we'll have a look at receiving the signal in a moment. All right, so when we're receiving the signal, we use this picket fence analogy. All right, so on this side, so if we've sent a signal up and down, and we want to send and through a picket fence, so it fits originally when we're transmitting it through that picket fence up and down. All right, when we're receiving it, we need to receive with an antenna in the same direction so it can go through. If we don't, it just gets muted out like this. All right. So what we say is the receiving rods must be aligned in the direction of the polarized wave. So we say waves are polarized in the direction of the electric field. All right. So what that means is when we were looking up here at our profile, we've got our, let's maybe have a look at this one. We've got our electric field in red. So that means if we've created electric field upwards in red, we have to receive it upwards in red. So whichever way the electric field's going, we say that's polarized that way, and we have to have the receiver going the same way. And basically what happens is exactly the same thing. These waves come in and in the antenna, they cause the particles to oscillate up and down, and we can translate that back into information, and that's how we get our Wi-Fi, how we get our TV, how we get all of those things that are transmitted and received. All right, so just in saying that, we normally polarize in the city. We will polarize for our TV reception the same way. In the country, they polarize the other way. So you might have noticed that in the country they have different stations. I think it's like instead of channel 9, they've got WIN. Right? They polarize the opposite direction so that their waves don't interfere with the city waves. They can transfer without interference. So that's a really, really cool little feature. So that's all I really want to go through today. It's just a little kind of a standalone introduction to electromagnetic fields, this little part. So next time we'll go on to something a bit different. But yeah, thank you.